which is Dmitry Tegunov. So if Dmitry can start sharing his slides and start his video. So Dmitry comes to us from the Max Planck Institute for Biophysical Chemistry in Göttingen. So he studied at the Technical University in Munich and started his EM career also in Munich in the lab of Seville Weinkauf. Then he moved on to Frederick Foster's lab at Martinsried, and he's currently in Göttingen in the lab of Patrick Kramer, where he develops Warp, which is this lovely software for doing on-the-fly processing that a lot of labs use. So today he's going to talk to us how you can use Warp for your cryotomography needs. So your slides are up. You can go ahead, Dmitry. Thank you.
Well, thank you so much. And I'm very happy to welcome all, I think, 900 currently of you to my humble apartment in Göttingen. So make yourselves comfortable, grab a drink. I hope I have enough drinks for everyone. And if we maybe practice dancing signal packing instead of social distancing, we might even fit in. So since you're all here, I would like to tell you about a new piece of software called M. Now, the problem that M addresses is that when we try to get high-resolution structures from in situ tilt series data, more often than not, they look like this. But as we know from in vitro samples, they can look at least as good as this, and quite often even much better. So what is the problem with getting high resolution out of in situ tilt series data? So ideally, tomography works like this. We tilt the object, acquire images at different angles, and then we can reconstruct that and average some of the particles. Unfortunately, in the real world, while we image the object, it changes because the stage is not very stable, beam-induced motion comes in, and so on. And even though we can correct some of that motion in the individual tilt movies, we still end up with this large-scale slow motion in the data. Now, if we wanted to correct this, we could try to track the motion, like here, for example, with fiducials. And sure enough, we can place gold fiducials into our samples and then try to track them, assuming they're perfect spheres. But usually this does not work with high accuracy, and it's also very hard to distribute them uniformly inside the sample. And for in situ samples, it's often even impossible to put them into the sample. But luckily, our in situ samples have plenty of natural fiducials, like the pattern on the skin here. Those are the proteins themselves. And so the way M makes use of this is this. So one of the main assumptions behind single particle average is that, in fact, we treat each particle as a single particle in isolation, and then we run its own tiny optimization for every single particle, and then we average them using those optimized parameters. Now, what M implements is what we call multi-particle refinement. We model all the contents of a tomogram or of a 2D micrograph as a multi-particle system. And we optimize the poses of the individual particles as well as the hyperparameters of this multi-particle system simultaneously in one single optimization. And some of these hyperparameters look like this. On one hand, we have global, pretty much per tilt or per frame in case of 2D data, movement because of stage instability, also global rotation for the same reason. Because of beam-induced motion, we have image space warping. if we have a fairly thick volume, then this image space warping could also be distinguished from volume space warping, where basically multiple layers of particles shift relatively to each other in the sample plane. And in the case of conventional 2D data, we probably quite often have domain, where the ice layer basically bends while it is irradiated by electrons. And so M implements this multi-particle refinement among many other improvements. And this is how it fits into the entire processing pipeline. So data come out of the microscope, either tilt series or frame series. And during this talk, I'm going to refer to what is commonly referred to as single particle data as frame series, because I find it rather unfortunate to reserve single particle just for 2D data. It's still single particle analysis if it's tilt series. And then those data go into warp, which some of you are already familiar with. Now, starting with the next major release, warp 1.1, it will implement the same feature set for on-the-fly processing for tilt series data as it currently does for frame series data. And once warp is done with all the pre-processing, once the movies and tilt series are aligned, CTFs are estimated, particles are picked, it exports the particle data and their metadata, such as CTF. Or in case of tilt series data, it exports subtomograms, which can then be processed in Reliant, where you have a wide range of options, such as 2D classification, ab initio map generation, 3D classification, 3D refinement, and so on. And once you're done with the global alignments of the particles and the classification, you can take all of those classes and those particle poses and export them into M. And then M performs further refinement, now not only optimizing the particle poses individually, but also optimizing those hyperparameters of the multi-particle system. Then it reconstructs the maps, and hopefully after one or several rounds in this accelerator ring, your particles fly out as really nice maps at high resolution. And so I know I promised to talk about new tools for tilt series, but historically, the development of M started with frame series refinement. And so one nice result that we got out of this was for the Epiferton dataset acquired on the new gel cryo-arm microscope, which had been previously published at 1.54 angstrom. At that point, it was the highest resolution cryo-EM map. Now, using M and some of its new features, we were able to improve that to 1.42 angstrom. Now, I don't mean to imply that this is a resolution range that will be relevant for most of biological projects, but this is just to show that you can expect at least the same resolution even in the highest resolution range as you currently can from the line. Now, a feature that is more unique to M at this point is multi-species refinement. Quite often you have quite high heterogeneity in your sample, and once you've classified out all of the conformations that you're not interested in, you're usually left with not so many particles per micrograph. And to optimize all of those hyperparameters of this multi-particle system, it is best to have as many particles in the system as possible so you can use all of that signal. And if you're only left with, say, 5% of your particles, then this optimization will not be very accurate. Instead, what I simulated here by artificially dividing those epiferritin particles into populations, you can refine both of these species simultaneously. And by doing so, you get more accurate estimates for the hyperparameters. So the same particles from the 5% species that previously went to 3.2 angstrom now went to 2.8 angstrom. So same particles, none of the 95% species particles went into that. They were just used in the hyperparameter optimization. Another thing that is increasingly popular now is filtering the maps to local resolution during 3D refinement. We already saw one of the current solutions in Side Splitter a few days ago here. And another approach is the non-uniform refinement in CryoSpark. And M takes a somewhat different approach here. Instead of using some FSC or explicitly SNR-based solutions, it simply trains a noise-to-noise based denoising model on the two half maps that we get from the particles. Now, we pioneered the use of noise-to-noise denoising for raw cryo-EM data in WARP pretty much immediately after the noise-to-noise paper came out. But so far that has been limited to raw 2D and tilt series data. So here we take the same basic unit architecture and we feed it one of the half maps, and we ask it to generate something as similar as possible to the other half map as its output. And as we train it learns not to just generate the average of those two half maps because there are just not enough parameters in this deep learning model. Instead, it learns to denoise the map, which is a very nice side effect, which I did not expect when I first started this. And the denoised map is also very nicely, very smoothly filtered to essentially the local resolution. Now, when I first saw that result, I think it was about 1.5 years ago, first I was very, very sad because all of the work that I had invested prior to that into figuring out how to do this with local FSC was pretty much obsolete because this deep learning based model learned all of that by itself, basically within just a few minutes. On the other hand, I was, of course, quite happy because it worked very well. So you have to imagine this neural network, it doesn't know about the existence of FSC, has never heard any discussions about the correct FSC thresholds. It doesn't even know who Marin is. So, and yet it manages to filter the maps very nicely to local resolution. Now, as promised, M for tilt series, this can use the very same features that you already saw for the frame series data, but now it's applied to tilt series. The first thing we did, we benchmarked M's tilt series performance on some data sets that were already processed with the currently best solutions, such as the latest EMEM version and EM Clarity. And in all of these cases, M, I would say, did quite well compared to the previous results. Those other packages, as far as I understand, they implement similar ideas, especially in the case of EM clarity. In the case of EMAN, I think they just basically take the individual 2D particles from the tilt series and refine them without any constraints. But EM clarity has constraints, so it is able to reach probably higher resolution than EMAN, but still, even compared to that, M does quite well. And when I saw that M works reasonably well for frame series and tilt series, I asked myself whether if we collected data in the very same way for frame series and tilt series, so exactly the same sample, adjacent holes, the collection, so as similar in terms of quality as possible, if we could see any difference in resolution. So I asked my colleague Christian to do that. And he collected tons and tons of epiferritin. And as you can see, both frame series and tilt series data went to pretty much exactly the same resolution here. And I've probably already taken a guess at which row shows what here. So here is the solution. I mean, if you didn't have those labels, I think it would be pretty much impossible to distinguish them. So the conclusion here is that if you can collect as many tilt series as you can collect frame series, then using M, you can expect pretty much the same resolution from both. Now, of course, tilt series are much, much slower to collect, but luckily, people like, I think, Martin Pillhofer and others are working hard to solve that problem as well. So maybe one day tilt series speed will at least somewhat approach frame series acquisition speed. Now about in situ. So far I've only shown you results for in vitro samples, but I promised in situ. So here it comes. Last summer I was approached by my former colleague, Julia Mohammed, and she was setting up her own lab, and she was looking for a new, robust, high-resolution pipeline for tilt series analysis. And they had collected a very interesting data set where they took whole AMP pneumonia cells, put them on a grid, and those AMP pneumonia cells, they are tiny enough so you don't have to fib mill them. So you can basically put them on a grid and collect data right away. And at the end of the summer, then we got some results which I originally definitely did not expect. Using M, we refined these in situ data to 3.7 angstrom. So we took all the 70S ribosomes in there, about 24,000 of them. The sample is about as thick as you would expect for in situ lamella of bigger cells. And I think the improvement in resolution here is quite striking. Now to prove that this is in fact 3.7 angstrom, here are some details. And I think they all live up to the resolution we claim. And one particularly interesting thing here is that they stalled those 70S ribosomes with chloramphenicol. And at this resolution, we were able to observe this chloramphenicol molecule directly inside the map. Now, as a control, here you can see a map from non-stalled ribosomes. This is still a bit lower resolution. It was refined with an earlier version of M. But still, I think we can see clearly that chloramphenicol can be distinguished in this map. And as far as I know, this is pretty much the first time that anyone has observed a drug binding exactly where it is supposed to bind inside the pathogen. Now, going from here, I mean, if you told me a year ago that we would have 3.7 angstrom from in situ data now, I would probably not have believed it. I thought it would still take quite a bit longer until we reach that level of resolution in situ. So what does this mean for the future? Now, I think the way forward here will be very different from what we saw for in vitro frame series data, where ribosomes were also some of the very first molecules solved to very high resolution by single particle analysis. But then moving on to smaller proteins, which are less abundant in cells, was quite, well, not straightforward, but definitely possible, as we see now. Whereas in situ, ribosomes are very, very special in their properties, and all of these properties are very favorable towards in situ sample data collection. They're huge, so that certainly helps with thick ice. And there are so many of them inside the cells. So we don't run into problems with low numbers of particles. Doing the same thing for pretty much any other protein inside the cell will be much harder at this point, I think. And I very much hope that we can move on to smaller and less abundant targets at similar resolutions in the future, but I think it will be a lot of work to get there. Now, I promised you not one, but several tools for in situ data analysis. And initially, I wanted to show you some tools that we've developed for heterogeneity analysis with 3D principal component analysis and autoencoders, and a nice piece of software used to visualize and analyze those results further. But I think it's a bit too much for today, and instead I will show you something that is already actually quite old, but I don't get to talk about this very often. So this is a piece of software that I wrote for visualizing the organization of membranes in situ. So usually if you acquire an in situ tomogram and you want to look at those membranes, you have a big problem. That is, those membranes are not perfectly flat. So you cannot really find an angle inside this volume where you can just put a 2D plane through the volume and look exactly at the membrane as it lies flat in the image plane. And my former colleague, Ben Engel, and his team, they had these very nice data of thylakoid membranes that are, as you know, involved in photosynthesis. And to be able to do photosynthesis, proteins need to be organized in some very intricate ways inside those membranes. So I really wanted to know how exactly those proteins are organized there. And so I wrote Membranorama, and it lets you take a segmented membrane and then fully interactively project the local tomogram density onto this membrane surface. And again, interactively, you can somewhat step away from this membrane surface to visualize adjacent regions to the membrane. You can use this to, again, fully interactively annotate the membrane. For example, here, placing one of the components of the photosystem on this thylakoid membrane. And using this tool, we recently published a paper with very elaborate analysis of those thylakoid membranes. And as you can see here on the right, the software also lets you planarize the membranes and then align the views of several adjacent membranes or different sides of the same membrane. So you can make these nice overlays, like you can see here, to see whether the proteins are in fact somehow organized between the individual membranes. So with this, I would like to thank Patrick for almost unconditionally supporting me. This has been extremely helpful in pursuing all of these goals. And our facility manager, Christian, he has collected tons and tons of epifertin for me. I'm very thankful for that. And our collaborators in Julia's lab, Julia and Leanne, who have provided really mind-blowing in situ tilt series data. And of course, also my former colleagues from the Baumeister lab. Ben Engel is now an independent group leader at Helmholtz. They really made Membranorama shine. And I really wanted to have released and preprint online before this talk, but then Corona canceled that plan, at least for the time being. But it will be out very, very soon, I can promise that. But if you're interested in using Warp, Membranorama, or other pieces of software, you can look those up in my GitHub repository. And I've been trying this new Twitter thing. I don't know, have you heard of that? There are quite a few cryo-EM people on Twitter. And they're having very civilized discussions about FSC and other fun topics. So you should definitely join us. And I will be happy to take your questions.
Thank you, Dmitry. Thank you. It is Friday, so it is time for an FSC weekend. It's been a while. So we've got a lot of questions for you, as you can imagine. First question is from one of our panelists. How do Warp and M pass on the improved knowledge of the particle positions and orientations into RELION?
So M and Warp share the very same data model. So whatever comes out of Warp, M can improve, and whatever improvements come out of M, Warp can read, and then use it in its particle and subtomogram export routines, which then deliver improved alignments to RELION. And this especially makes sense if you think that your initial alignments were very bad. Then you might want to reclassify your particles. But usually for simpler data sets, you don't really need to go back to RELION. You can just end the whole process in M.
Okay, and a further question. This is from Colin again. Does the noise-to-noise denoising in M use half sets of particles or odd and even movie frames like in Topaz?
It uses just the usual half maps. I mean, this is basically what noise-to-noise needs to independently noisy pieces of data showing the very same thing. And single particle analysis has had those two pieces of data since pretty much the very beginning.
Okay. A couple of similar questions from Liz Kellogg and Katerina Nadinova. Can you see what kinds of deformations are dominant contributors to the loss of image resolution? Is it doming or warping? Which of those motions do you see more prevalent?
Mm-hmm. So for frame series data, doming, at least in the data that I've analyzed so far, has barely ever improved anything. But this is also because we fractionate the dose very coarsely. And you may have seen a preprint from John Rubinstein's lab a few days ago, where they propose a new file format that lets you fractionate the dose much more finely with Falcon cameras. And for tilt series data, the most significant misalignments are just global translation and rotation. Everything else gives you maybe an extra, I don't know, 10 to 20%.
Okay, thank you. So we have to move on to our next talk, but thank you, Dmitry, again. And I hope you can answer the rest of the questions in the Q&A section.